So we're still on Chapter 6 review here. We're talking about number 15. Two skaters initially at rest, push against each other, and they move in opposite directions. What's the total momentum of the two skaters when they begin moving? Well, if they're initially at rest, the total momentum initially was 0. Therefore, the total momentum afterwards would also be 0. So it doesn't matter what size the two skaters are. They're going to have equal momentum. If one is bigger, that person will go slower. If one's smaller, the other will go faster. Number 17, explain how momentum is conserved when a ball bounces on the floor. So momentum is conserved right here, VI, VI, VF, VF. Momentum is conserved because, well, you see when the ball hits the floor, it's got some momentum. And when the ball bounces back, it's got some momentum. And I know this is crazy to think about, but the Earth also does recoil when the ball hits it, except for the Earth is really big compared to a ball, unless your ball is the size of like the moon. And so because the Earth is so large, the velocity is incredibly small, and so the momentum gets conserved. Number 18, same exact thing. The ball falls towards the Earth, momentum increases. The momentum of the ball increases. What about, conservation? Well, the Earth does move towards the ball. You just don't notice it because it's so darn big. Number 19, they used to think that rockets couldn't fly in space. How does that work? Well, it's actually the momentum of the stuff coming out of the gun is equal to the momentum backwards of the gun. And that's how it works out in space. If you were to throw a bunch of marbles, you'd move. Number 23. Now we have actually a math. So we've got a tennis ball launcher. And so they give us this thing is sitting still. So initially, the velocities are 0 for both of them. So final, though, now you've got a 55 kilogram ball, 55 kilogram machine, 55 kilograms, and we'd like to know how fast it is going. And the ball has a mass of 0.057 kilograms, and it's traveling at 36 meters per second. And so what you're going to do is you're going to solve for VF right there. I'm going to let you figure that one out on your own. I'm not going to write out the answer to it. After that comes number 26, and it's a concept. When you have an elastic collision between two objects, do both objects have the same kinetic energy after the collision? It's an elastic collision, so yes, they have the same the total kinetic energy before and after is the same. The two objects may not have the same kinetic energy as they individually did, but the total kinetic energy will be the same both before and after the collision. And then number 28, two carts with masses, so I did 26 and 28 here. Two carts with masses of 3 and 4 kilograms move towards each other with frictionless tracks with speeds of 5 and 4. The carts stick together after a head-on collision, find the final speed. And so here you're doing the other equation where you say mvi plus mvi of the two carts is equal to the mass plus the mass times the final velocity of both of them. And so you've got 4 kilograms and 5 meters per second and 3 kilograms and 4 meters per second. And so that's 20, and then this is, it's a head-on collision. Move towards each other, head-on collision. And so this is 20, and this is be negative 12, and so you get a total of 8 there, equals the mass and the mass, which is 4 and 3 times VF, and I think from that point on you can solve it without me. And that is enough for this one.